We're now going to shift our focus in this course to talking about programming languages and interpreters, where an interpreter is a program that takes as input the code written in a programming language and executes that code in order to create the behavior described by the program. And there are many different programming languages that have been invented over time. And so far in this course, we've talked about Python a great deal and Scheme a little bit. I taught you about Scheme for two reasons. One, it's a delightfully useful, simple, and effective programming language that still gets used today, even for new projects. And it's a dialect of Lisp, which is used even more broadly, either as a standalone application development language or as an embedded language that implements part of a program that also uses some other language. But the second reason is that it is a programming language that's very powerful but has few rules. And so you will be able to build an interpreter for the Scheme language by writing down a Python program that describes all of the rules of interpretation for the language. And interpreters bring together many ideas in this course. Programs are trees, and the way interpreters work is through tree recursion. Expressions often have lists of sub-expressions. The input to an interpreter is another program, which is kind of like a higher order function. And interpreters can be modular and extensible. Part of your interpreter program will describe how interpretation works generally, and another part will encapsulate all the details of how the different parts of the language actually execute. So with that introduction, let's talk a little bit about programming languages. A computer typically executes programs written in many different programming languages. There are what are called machine languages. In machine languages, the statements are interpreted by the hardware itself. Computers have a central processing unit, which can execute a fixed set of instructions and has a limited availability of its own memory and then ways to access more memory in the caches and main memory and disks of the computer. But to extend a machine language, you actually have to change the circuitry of the computer, which does not happen very often. These languages are hard to program in. Operations refer to specific hardware memory addresses, and there's basically no abstraction mechanism, no way to give things names, and no way to implement procedures or functions. That's all left to high-level languages, which have statements and expressions that are interpreted by another program, or they're compiled into another language. Interpreting involves reading the program and executing its behavior, while compiling involves translating it into another language, such as a machine language, so that it can be executed later. And many modern languages do a mixture of both of these, compiling parts just in time in order to be executed as if they were being interpreted interactively. But those details you can worry about in a later course. The important part is to know that high-level languages provide means of abstraction, such as giving names to values and functions and objects and classes. That's all part of high-level languages. Now, people describe different levels of height. Some languages are higher level than others, but those details you could try to study in later classes. The important thing to know is that there isn't a piece of hardware in your computer that was designed for Scheme or Python. Instead, machine language code needs to actually execute all of the behavior, and an interpreter or compiler in between the high-level language like Python or Scheme and the low-level machine language needs to implement all of these means of abstraction. But it's very common that high-level languages will be built on top of other high-level languages. A machine language might be used to implement a compiler for the C language, which is a high-level language used to build the interpreter for Python, for example. High-level languages are easy to program in because they provide means of abstraction, and they also abstract away certain system details so that you can write the same program and have it run on different machines made by different hardware manufacturers, or run inside different operating systems created by different companies or organizations. In Python, what happens is that it's actually compiled just before it's run into something called Python 3 byte code. You can see this byte code using the dis module that's built into Python. And then there's an interpreter that runs this lower level language, which is quite similar to a machine language, but also abstracts away some system details. So the story of how a program in a programming language gets executed can be kind of complicated, but the distinction between what your machine can execute and what you as a human tend to write is an important one. Everything we've learned in this course is about high-level languages that are used to build software today. Sometimes people invent new programming languages. A powerful form of abstraction is to define a new language that is tailored to a particular type of application or a particular problem domain. For example, there's a programming language called Erlang that was designed for concurrent programs. How is it the case that people can use ATMs all around the world and the balance of their bank account is stored in some particular place, but if you try to withdraw money from 2 different ATMs in 2 different cities for the same bank account at the same time, there's no way to trick it into paying you twice? That's a kind of concurrent communication problem that would benefit from having a specialized programming language. And Erlang is also used, for example, to implement chat servers with many simultaneous connections, where lots of people are talking to lots of other people, and the program has to keep it all straight. Another problem-specific language is the MediaWiki markup language, which was designed for generating static web pages that you see on Wikipedia. It has built-in elements for formatting text, linking one page to another, and stitching together multiple pages into one so that a large page can be broken out into modular components. It's a programming language, perhaps not as full-featured as Python or Scheme, but it still needs an interpreter or compiler in order to be used to generate the Wikipedia pages that people read. A programming language has a syntax, which is the description of all legal statements and expressions in the language. So that's the form of the language. And then also the semantics, which is the execution or evaluation rules for all of those statements and expressions, the meaning of the language. And these two together give you a programming language. To create a new programming language, you either need to write down a formal specification as a document that describes the precise syntax and semantics of the language, or you need to build an implementation of an interpreter or compiler for the language which serves as the reference to describe the syntax and semantics. Any input into the canonical implementation that doesn't cause it to crash would be legal syntax, and its behavior would define the semantics. Scheme is a language that started with a specification, and an implementation of the interpreter came later. Python began as a canonical implementation, and then a formal description of how it works was developed over time based on that implementation. Most programming languages that are used in practice for large communities have both a specification and an implementation.